Qwen 3.8-27B. This is the best local model that you can run on consumer hardware. And it's really great for its size. In this video, I'm going to show you how to combine this with a powerful coding agent like DeepSeek Harness to build powerful agentic systems. And it also has some really interesting hidden capabilities. For example, it's really great at image understanding and drawing bounding boxes. So in this video, my goal is to show you how to set this up. What are the different configurations that you want to be using if you want to use this model, and also mistakes a lot of people are using for inference. To start off, we're going to look at just a couple of different benchmarks because this really shows you how powerful this model is. So here's the artificial intelligence agentic index. Right now it's at 51, which actually is just behind Qwen 3. Qwen 3 is a 2.8 trillion parameter model. The most important thing is that the performance actually holds up in real world testing. And I'll show you a few examples later in the video. Now, to put it in perspective, intelligence or performance is very close to Claude 4.8 on max setting, which was state-of-the-art model just a few months ago. Now, one could argue this is probably benchmarked, but the real world performance is actually really great. I'm going to show you how to set this up with the DeepSeek Harness, which in itself I think is a very interesting innovation, especially coming from DeepSeek. It's a very powerful harness and I have been having a lot of fun with it. Their core idea is everything is plugin. I created a video on it. I'll highly recommend to watch that to get started. Okay, but before that, I'll talk about where you can get the model. So it's already available on Hugging Face. If you have Apple Silicon, then I'll recommend to use the MLX version. And if you want to run this on Linux or Windows, VLLM and Stelang are two options that you want to try. So right now I am on DGX Spark. I'm going to be running the NVFP4 version. I have a cluster of 2 nodes. Now, DGX Sparks are not really designed for running the 27 billion dense model. So I'm getting about 15 to 20 tokens per second on single thread. On concurrency, I think I get up to 60 to 70 tokens per second, which is pretty usable. Now, in order to run the model, you can simply run this. It's going to set up the server for you, and you can access it over the network. This basically downloads the model for you along with the drafter model, which enables speculative decoding. Okay, so for inference, I already downloaded the DeepSeek Harness. I created a video on it. I'll highly recommend to watch it to get a sense of the basics. Okay, so here's how the harness looks like. Now, in order to set up the Qwen model, I had to go through settings. And then within settings, you can actually configure any model of your choice. So you just need to go to the open configuration file. This is going to open this YAML file for you. Now, within this YAML file, you need to define your provider. So I've been experimenting with the different models. So you can see here's a DeepSeek V4 Flash that was running on that cluster. There's even 3.8-27B MLX version. But right now I am using this configuration, which is running it on 2 DGX Sparks. And the reason is that I wanted to use that full context window with multiple concurrent requests. Now, you probably have seen the coding capabilities, so I'm going to start with what I found to be the most interesting one. So I provided this image. This is a reference image. It's a multimodal model. It means it can understand images and text. Now, in here, I basically asked it to describe what exactly it sees in the image, and it actually goes into a lot of details. The description that it produced is pretty accurate. I asked it to use OpenCV, which is a Python package for computer vision. Let it decide to do some analysis. So it actually wrote its own harness analyzing raccoon image. Now, since this was pretty open-ended, so it did quite a few things. So for example, here it's looking at edge detection. This is doing some type of corner overlay, is to identify corners in the images. Now, this is running entirely local on the DGX cluster. Thanks to NVIDIA for sponsoring the compute. These vision language models are really great at identifying objects, but they're really bad at counting. But This model actually surprised me. So I said, how many cars do you see in this image? And it counted a total of 26 cars in the image. So I thought it probably just made up a number. But then it says, okay, starting with the top row, which basically is here. And if you can count the car 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So it counted a total of 11 cars. Then it's talking about the main lot, where we can actually see there are 1, 2, 3, 4, 5, 6, 7, 8, 9 cars. Now, for some reason, it didn't count this row as a part of the main lot, but the counting turned out to be pretty accurate. Now, for this, we need to look at the chain of thought. So it seems like it's able to divide the image into different patches of variable size, and then it's able to identify objects and count them within those patches. So it's not just identifying objects, but it's able to point at them. We have seen this capability with the DeepSeek vision model paper, but haven't really seen this in the wild. Okay, but then it gets actually even more interesting. So I said how many white cars are in the image. Then it again started counting exactly the way it did before. So it divides and looks at the top row, then the main lot, and then curb. So according to it, there are a total of 8 different white cars. Now, if you go to the original image, there seems to be 1, 2, 3, 4, 5 white cars, but it definitely added this, and I think this. But then I said, okay, what if I asked it to draw bounding boxes around the objects? But the interesting thing was to see the actual results. Now, in order to do that, it actually wrote a Python program. So the coordinates of the bounding boxes that you are seeing, these are coming directly from the model. So the model is actually pointing to different objects in the image and then just drawing bounding boxes on top of that. Okay, so here are the results. And it's actually pretty impressive, especially that is a vision language model drawing bounding boxes just by looking at the image. Now, they're not perfect, right? So if you look at these, probably it's covering a lot more area, but in general, it's really accurate. Now, one could argue about these two or even the pickup truck case. However, I think you could say that they pass. Now, you could add another model which basically does object detection, and then you can use this model to say whether these detected objects are accurate or not. But in general, I'm really impressed. I haven't seen a vision language model this accurate on bounding boxes for multiple different objects of different orientations. And keep in mind, it's not using any external tools, which makes it even more impressive. Okay, so some other tests that I ran. So here is a result of real-time International Space Station tracker. It actually is one of the best outputs that I have seen from an open model. Really impressive work here. And it's pretty accurate in terms of the real-time updates. It does it every 5 seconds, exactly the way we asked. But the quality of the output is going to really be dependent on the reasoning effort that you set. Now, next, we need to talk about the reasoning efforts. There are 4 different levels: completely off, which becomes a non-reasoning model, then low, medium, and extra high. There's no high. Now, you need to be very careful when you select the reasoning efforts, because it can overthink a lot. And I mean by a lot. Sometimes when you set it on extra high or medium, it will use the entire completion budget as thinking budget, and you're not going to get anything as an output. And I have seen this happen to me quite a few times. So for completely off, I asked it to create a website about itself using web search. So the output tokens were about 20,000 tokens. Now here are the results of same prompt for 4 different thinking levels. So this one is completely off. You can actually see that it just made up some numbers. I asked the model to do web search in a harness that it hasn't seen before, and then create a website explaining everything. Now, this is AI slop that you would expect from a small local model. But then just by changing the reasoning effort to low, it actually started to generate some really interesting results. This is actually a pretty nice website. I argue that It's even better than something like GPT 5.5 when it was initially released. There is that bluish tint still, but overall the visuals are really nice. Now, here are the results when you crank up the thinking budget to medium. Now, it started adding these nice animations. I think the quality improved significantly compared to completely off reasoning, right? So you can see substantial improvement. However, the number of tokens that it used was substantially more compared to the non-thinking one. And finally, same prompt, same context is extra high reasoning. You can actually see we get much better results. The visual quality is pretty great. Animations are very similar to the medium reasoning, but the visual language is a little different. The colors are different compared to the low and medium. For some reason, they used pretty consistent colors. Now, I had another go on extra high, and here are the results. Seems like the reasoning has a lot to do with what the output theme is going to look like. And I think this is a pretty usable website that you can get out of a local model. Now, a quick look at the out of tokens. So for reasoning off, input tokens were 82,000 tokens, output are about 20,000 tokens, and it took around 15 minutes. The per second are about 25, but it varies between run to run because it's running multiple concurrent models. With extra high, it's almost 500,000 tokens input, 60,000 output tokens with around 86 minutes. Now, medium, for some reason, actually consumes a lot more tokens. So it's almost 860,000 tokens with 38,000 output tokens. And it also took about 63 minutes. Reasoning, 35 minutes, 170,000 tokens input, and about 31,000 output tokens, right? So you can see if you crank up the reasoning effort, the number of tokens basically explodes. Now, this is happening under a completely new harness, which I don't think the agent has seen before. This is DeepSeek Harness, but it has this really neat feature of trajectory. So you can click on this, and this basically shows you everything that has happened so far in the context. So we have the initial system prompt. Everything is auditable. You can actually see what exactly went into the system prompt. Then what was the user message? This was my initial message to the system. Then the context, and this is the initial context that the model has for DeepSeek Harness. Now, some of this is not relevant to the Qwen model, but it still sees those. So these are all the lists of skills that is available, right? But then the beauty is that you can actually see what exactly the actions the model took. If there are tool calls, you can see what exactly the payloads were, what is the schema it was using, the results, the timing, which is pretty incredible. Like I haven't seen any other harness provide you this level of details. Usually you need to use some other tracing tool for observability, but DeepSeek enables you to actually look at all the actions that were taken along with a timeline. So you can audit it, you can figure out where the agent is failing, and then you can even update your tools if you see multiple tool calls are failing, which is pretty incredible. Now, I do plan to create a dedicated video on exploring this plugging mechanism in the DeepSeek harness. I feel like this is a very new take on harness design, and a lot of people can learn from it. Okay, by the way, it has just crossed 160,000 GitHub stars. It's less than a week old, which is crazy. At the moment, I think this is the fastest growing open source project on GitHub in its entire history. Now, the funny thing is that they are not accepting any external contributions. So all of this is thanks to the DeepSeek team. Okay, I'm going to be running some more experiments, especially with the visual analysis capabilities, because I think I haven't seen anything like this. But do check it out and let me know if you have any specific questions. Anyways, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.